Good morning, folks. It is 2 days before the deadline for homework 3. That's Sunday at midnight, just to remind you. That's one announcement. Another one is, I've been geeking it up the last couple of days with the development boards, and finally plugged in and used the port expander. So I got an example running of the keypad using the port expander rather than the main CPU, which frees up some connections on the main CPU because the port expander is driven off the same SPI port as the DAC. So, yes?
Which physical pins on the development board is the port expander supposed to?
Physical pins have unique names, port Y and port Z. So there's two named 8-bit ports on this end of the board that are not used for anything else. So in this case, the keypad is connected to port Y and the second example connected to port Y with a shift key. So now you have 24 button pushes possible rather than 12. So I used one 8-bit port to implement a 12 key keypad plus a shift key. That was fun. The only thing that was really challenging is that the DAC is being run in an interrupt service routine 100,000 times a second, uses the same SPI channel as the keyboard expander. Keyboard expander takes about 6 SPI transactions to load a port and read a port. So in the middle of loading and reading a port, interrupt happens, the DAC trashes the state of the SPI channel, and then we go back to the reading the keyboard, and guess what? It doesn't work. So I had to write a critical section controller so that for the few microseconds it takes to actually read the keypad, it's treated as a critical section. You all know the words critical section in code? It means nobody's allowed to interrupt it, no exceptions are allowed to occur, no interrupts are allowed to occur. So make that a critical section, everything works. That might be useful for final projects. Might not. Need to go back and talk now about Lab 3. We talked about dynamics. We talked about fixed point pretty quickly. Talked about direct memory access last time. Again, pretty quickly because there's lots to go through. There's one more topic that we need to do for the homework, and that's setting up an ADC. So, but first, before I do that, are there questions about direct memory access? Direct memory access is a scheme, uses a separate processor to move data. So moving data is a very commonplace activity to perform in a program. It's so commonplace, it's worthwhile having a coprocessor, a separate piece of hardware, which does it for you. So you don't have to program it. So in terms of, again, the layout, you have a instruction generator, address generator, and a data address generator that can read the system bus. This is not a bus exactly, it's actually a switch matrix, and it can read flash, data, or peripheral. Oh, does that mean you can execute code from RAM? Yes, in fact you can. But for the purposes of this exercise, there is another source for addresses to the system bus for controlling the system bus, and those are the direct memory access channels. That is what you're going to be controlling for Lab 3. Now, one of the students thoughtfully pointed out to me that question 4 is stupid, which I appreciate. Write the code necessary to send 1 second of sound to the DAC described in Lab 3 at 8 kilohertz sample rate from a table 256 entries long using DMA and no interrupts. So the implication is that you're going to be traversing a table 256 entries long. This is not direct digital synthesis, folks. You're traversing the whole table. 256 entries long at a rate of about 2 to the 13th. 2 to the 13th samples per second divided by 2 to the 8th gives a frequency which is a whopping 2 to the 5th. Can you hear 2 to the 5th hertz? What frequency would that be? 32 hertz. You can hear it, but the speakers can't reproduce it. Are these speakers, these cheesy speakers we have in the lab, cut off at 150 hertz? So this is kind of a stupid program, but still, you can write the code for it. If you had it hooked to a rumble seat, you know, so you're doing sound effects, you were shaking the person, maybe that would make sense. Any other questions about homework 3, since it's up in front of your face at the moment? Yes?
What should we fill that table with? Just a sine wave, or is it totally irrelevant?
It's irrelevant. You can fill it with anything you want. So, yes, if it were a sine wave, what I said was true. But what if it was this? So if it was 1 cycle of a sine wave, it would be 32 hertz. But what if I had 20 cycles of a sine wave in there? Then you'd hear it. Then it'd be 600 hertz. Thank you. This table, or any table you play through DMA, is going to be the entire sound you want. So you could have a word stored in RAM, Zool. You could have numbers 1, 2, 3 stored as table entries, and play them back using DMA. But in any case, yeah, so it could be whatever you want in that table. Table can be longer than 256 too. It could be, who's read the documentation? What is the maximum size transfer for a DMA burst, for a DMA block? Has anybody read the documentation? It's slightly obscure. Turns out there's an error in the documentation that says that the maximum size is 256 bytes, and it's not true. If you look at the length of the register and count the bits, it's a 16-bit register. You can do 65,000 entries. You can have a table of 65,000 entries long and send it in with one instruction from the CPU. Enable DMA. It goes for 65,000 entries before it stops again. Any other questions on homework 3? Yes?
So if you, say, recorded a word and you wanted to convert it into a bunch of table entries that you could play, how would you even go about doing that?
Oh, so I thoughtfully did this a while back. Actually, I did it because I wanted to see if I could do something amazingly cheesy, and that is use the CV ref output as a 4-bit DAC. VREF is an A to D to A converter. So this is playing speech back through the DAC, through the 4-bit DAC using DMA, And I'm not going to tell you, but the main thing is that I wrote a WAV to table converter. That's actually fairly easy in MATLAB. So the MATLAB spits out a C header file, which gives you the header necessary to build a table to header file. Bink. Static, constant, unsigned car, all digits. So the fact that it's a constant means put it in flash. So this spits out a header that will encode a WAV file. And that's on the vref as a DAC page. I did that fairly early on. So the style of the code is not wonderful. Any other questions on homework 3? Due Sunday, 23:59 hours. Okay? Let's talk about ADC, analog digital converter. The ADC on this chip is a fairly vanilla analog to digital converter in the sense that it has a bunch of channels, AN0 through AN15, which map to random pins around the chip. So AN9 is RB15. I wrote code for AN11, which happens to be RB13, which is not used by any of the peripherals. They're scattered all over. AN0 through AN5 are over here on port B. But, and our chip doesn't have all 16 channels. It has, I don't know, 10 channels or so. There's a mux that chooses the channel you want to record from. There's a channel scan controller that allows you to automatically go through several channels in a row and push those onto a stack before you read them all back at the same time. So there's sort of a little bit of automatic channel scanning here, which I haven't played very much with. And then there's a reference input, which can be set either to VReference low or to analog input 1. If you hook analog input 1 to the reference, then you have made a difference amplifier here, allowing you to measure differential voltages. Why might you want to have a differential amplifier? Well, there's noise cancellation, of course. But if you put a shunt resistor across those, you could measure current. So having two inputs allows you to make current measurements as well as voltage measurements. So that's kind of cute. We go through a diff amp. This is an analog amplifier. This is an op amp. And into a sample and hold. The sample and hold does is to close a switch, and then when you say acquire, it opens the switch, freezes the voltage on the capacitor, which you then convert. This is necessary to get high resolution at high frequency. You have to be able to do a hold operation. Well, this implies a couple of things. One is it implies that it takes some finite amount of time to charge that capacitor from whatever source is in here. So there's sort of a maximum rate you can run the ADC. There's also a minimum rate you can run the ADC because the capacitor voltage starts to droop after a few hundred microseconds because of leakage resistances. So you have this whole thing should be timed to a few microseconds. And in fact, my code does a conversion in just under a microsecond. Pops the switch open and does the conversion in just under a microsecond, and you probably don't want to mess with that timing. You do not change the sample rate by changing the ADC timing, but rather when you start the acquire. So you're going to control when the acquire occurs, when the switch pops open, bink, that's going to start the conversion. Your code is going to control that. Then the conversion itself is a very straightforward successive approximation, 10-bit successive approximation, which is equivalent to a binary search. So it takes about 10 clock steps, where clock is analog to digital clock. It's yet another prescaler. Then you read the result out of a buffer, which can be filled up to 16 different values. So it's successive approximation. It is ten bits, but to get a megahertz actual conversion, to get a megahertz into memory, you must use direct memory access. You can't actually take interrupts at a megahertz. So you have to do direct memory access. There's actually 9 inputs on our package. Let's see. There's internal volt. I said all that. Oh yes, the conversion, there's an option for the conversion result to be in several different formats, 16-bit unsigned, and the scheme for the conversion is going to be that the voltage between 0 and Vref is going to be coded as 0 through 1023 counts linearly. Vref by default on our chip is 3.3 volts. It's actually VDD. You might want to measure that if on your particular chip, on your particular regulator, if you want very high accuracy. But basically, the output of the ADC is an integer between 0 and 1023. You can output it as signed, unsigned. Why in the world would you want a signed output? Remember that differential amplifier? If the negative input is bigger than the positive input, you'd get a negative output. So the signed option is necessary for differential input. You can specify that you want 32-bit accuracy. You still get 10 bits, but you have a whole bunch of leading zeros. Or you can go to fractional output, which puts it in some strange fixed point format, and I haven't tried that.
Question?
Yeah.
So the output from an ADC can be anywhere from 0 to 1023. Right?
Correct, bits.
So
Yeah,
like,
10 bits.
For some like words, like would that be high enough resolution? Like for some string of sound, or what you're saying?
Well, that's an interesting question. So 10 bits is not really what you call high fidelity sound. So you can turn it around and you say, at what point does speech become unrecognizable? If the sample rate is high enough, you only need 1 bit. At 8 kilohertz, you can actually understand 1 bit speech. Sounds pretty robotic. Sounds pretty nasty, but you can understand it. 4 bits is completely understandable. So 10 bits is not so bad for routine measurements. that gives you 0.1% accuracy if you're thinking in terms of voltage. That's better than your digital voltmeter. It's also at a range where you have 300 counts per volt, so that's 3 millivolts per count. You have to ask yourself, what is the background noise on the measurement? It is very easy for an SPI channel, which just happens to be near the wires, not even connected to the wires, just near the wires, to induce 10 or 20 millivolts of noise onto an analog signal. So getting actually 10-bit accuracy in the presence of noise is hard. That's why a lot of microcontrollers have about 10 bits accuracy, because you just can't do better than that in the presence of all the noise that comes, spike noise that comes out of the CPU. So I wrote a little demo code here on the dev board page. So there's an ADC example, which is a very simple example. I'm not turning on any ADC interrupts. I'm reading the ADC in a thread because I'm only reading it fast enough for human interaction. And we're yielding this thread for about 60 milliseconds. So it's being read, what, 16.7 times a second or so. And so there's no particular reason to build an interrupt structure to do the reading, or to use DMA in this case, although you could. So the thread reads the analog digital converter, but let's go down to main where we set this mess up. And the ADC has a ton of parameters, which is what I want you to explain in the homework. We're going to close it. We're going to close ADC 10. ADC 10 means the 10-bit converter, implying that sometime later they might put a different converter in there. And what we're going to do is to define a bunch of parameters, and then at the bottom link all the parameters together into one gigantic turn on the open ADC with param 1 through param 5. So param 1, define param 1 as, we're going to say we want integer format 16. Okay, we're just going to have the minimum size integer. We're going to turn clock on to auto, which means it's always running, and we're going to turn ADC auto sampling off. What that means is that I have to manually start the acquire process in my code. If you had turned auto sample on, then as soon as a conversion finishes, the next one starts. In other words, the ADC runs as fast as possible. We're going to define the input parameters as vref goes from VDD to VSS, so 0 to VDD. Turning off the offset calibrate, turning off auto scan, turning off everything, samples per interrupt, don't care, don't have an interrupt, alternate buffer off, alternate input off. In other words, we're disabling all the special features in parameter 2. And the point of the homework is to get you to read the manual so you know what these all mean. Parameter 3 sets up the timing for the conversion. And let me tell you, if you can understand that, I'd like you to explain it to me. I effectively set up this parameter by trial and error because I could not understand the documentation until I wrote the code. So it was an iteration. Read it until I got tired of reading it, write some code. Didn't work. Read it some more, write some more code until it finally worked as fast as I could make it go. The timing is really hard to understand. Where a parameter 4 enables an analog input, in this case AN11. AN11 would be
It's right there, pin 24.
pin 24, AN11. RB13 on the board. We're going to skip, but we're not going to scan. And now, now we have to set a channel. So we're going to set channel 0 to be negative NREF. This is MUX channel 0 now. This is MUX channel 0. The negative is going to be NVREF, and the positive input is going to be AN11. And now we open the channel. If sometime in the future you want to read another channel, all you have to do is change the channel. You have to do a set channel. You don't have to close the ADC, reset anything else, merely change the channel. Once you've done all that junk, once you've defined the data format, defined the sample rate, defined the references, then all you have to do in the thread is read the ADC after you do the acquire. Why am I doing the acquire after I read the ADC? Because I'm starting a new conversion. I read the old conversion, I start the new conversion, I do all this other stuff. By the time I get back here after 60 milliseconds, the new value is ready. So quite often in my code, I will fold conditions to avoid waits. And this avoids any wait by folding it so that the acquire happens right after the read.
But you're delaying for 60 milliseconds in between each of these threads. Won't the capacitor have leaked out at all this voltage at that point?
The acquire starts the conversion, which finishes a microsecond later and stores the value in the buffer 0, which is then read 60 milliseconds later. So the conversion is long done.
Okay, so the acquire is not the hold. The acquire is the hold and the conversion.
The acquire starts the hold and conversion, both, yes.
Okay.
Everything is phase locked off of the acquire.
So after the acquire and the conversion, that value is, so not the voltage, but the converted value is stored somewhere that you're reading from the...
It is stored in the buffer right here. Stored in buffer 0. So the output of the ADC goes into buffer 0. And that is why we're reading 0 right there. It's buffer 0. It's not channel 0, it's buffer 0, which was loaded with the data from AN11. To play with fixed point arithmetic, I then converted this to a voltage in two different ways. The first is to define an ADC scale, which is a float to fix of 3.3 divided by 1023. So that represents the 3 millivolt per step of the ADC from 0 to 1023. So now we can do the conversion to float. We can do a float conversion saying ADC value times 3.3 divided by 1023 is a voltage. And we can do a V fixed version of that, a fixed point version, which says mult fix 16 of int to fixed 16 on the analog to digital value. That takes the integer 1023, 0 to 1023, converts it to a fixed point number, and then multiplies it by the ADC scale. Then to print this, we're going to build a print buffer which does a %d for the raw ADC value, does a %6.3f. What's that mean? 6.3f? Who's down in the bowels of C? Yes.
6 numbers, then the decimal point, then 3 numbers.
Right. So this says give it a field of 6, and then but terminate after 3 decimal places. That avoids having floats with 8 significant digits where you have no data. I really don't like to see that. So this truncates at millivolts. And then this peculiar thing is a %d period %03d. What does that do? Who wants to guess that one? Can you guess that
I
one?
think it pads it with zeros to keep the width eccentric.
So the second one, the 03d, pads to 0, pads with leading zeros. %d period %03d takes an integer, puts in a decimal point, and then pads out 3 digits. Okay? And what am I plotting there? I'm plotting in the %d fixed to int of v fixed, in other words, the integer part of the fixed point voltage, followed by 1,000 times that voltage. In other words, I'm truncating off the integer part and leaving only the decimal part, and then converting that to an int and presenting and printing it as a 03d. So this converts a fixed point number into a floating point presentation on the screen. That took some fiddling to get right. And, oh, by the way, because I got tired of doing this, every time you want to print a line, you have to write over it with black, and then you have to set the color and the text size, and then do all that stuff. I wrote a function which does that for you. So, huh? So in the TFT display page, there's this charming image in which shows that you can write any line number in any color with any background, so you can make it completely unreadable if you try hard. But the whole function is print line. You give it a line number, a logical line number, as if it's a terminal, the print buffer, the text color and the background color, and then you don't have to do all of that that clearing and all that. It's all hidden away from you in a tasteful function. So what you're going to do in lab 3 is about 30 times a second or so, or 15 times a second, about 15 times a second, you're going to read the ADC. You're going to read the ADC, much like the demo code. And then you're going to use that value to set the position on the screen from 0 to 239 of the control panel. So you're going to make a game controller.
So as far as drawing on the screen goes, I've noticed that when you clear the screen and then write stuff to it, it visibly flashes black when you write over it in black. So is there a good way to clear the screen and redraw everything without having that effect so that we can have smooth looking video?
So the question is, how do you avoid clearing the screen to black before you redraw everything? Because that's a slow operation. Because it has to redraw 320 times 240, which is a little over 70,000 pixels. The answer is don't do that. So what you could do is keep track of where the center, make this just a single line, boop, keep track of the center, erase that single line, and then redraw it up a little bit. Now what I've also seen people do is keep track of the part that has to be erased and only erase the part that has to be erased and only draw the new part. To my mind, that's not worth it. But what you're going to do is, for every ball on the screen, you're going to keep track of the position of the ball and erase it before you redraw it. So you're erasing individual balls and and the paddle, and never the whole screen. Otherwise it will flicker hideously, and you won't be able to make 15 hertz. You'll also find that if you erase the ball at the last possible moment, you'll get less flicker. So rather than erasing all the balls and redrawing all of the balls, which is really obvious because they all disappear and then they all reappear, erase one, rewrite it. Erase the next one, rewrite it. Erase the third one, rewrite it. So as you go through the list, as you go through, traverse the list of balls, erase the old position, update the position, draw the new position. That way you don't have to maintain a separate array of old values and new values. Erase, update, do the dynamics update, draw for that one ball.
Okay, and that dynamic updated ball is checking for collisions against every other ball and all the balls.
Mm-hmm. So you have to check every ball against every other ball on every time step. Luckily, the first step of that is fast. If we look at the pseudocode, the first step you do is find out if delta x and delta y between the two balls is less than 4. If both delta x and delta y are not less than 4, you don't do anything else here. So while it is an n-squared problem, because you have to check every ball against every other ball, the leading coefficient of the n-squared term is small. The dominant term is in n, because only about n balls will be within 4 of each other. So it does not scale like n squared, because the first check step is quick. Make sense? You know what I mean? Have no idea what I'm talking about? You know about order of complexity of computing? Things that go as n squared get bad fast. If we had to do the full intersection algorithm of every ball against every other ball, then if we double the number of balls, it takes 4 times as long. In fact, calculating the interaction of the ball is going to be like 0.01 n squared plus 1n. There is an n squared term corresponding to every time you have to do the intersection, but only 1% or so of the balls are going to intersect on any given time step, and so that is a fairly small term.
Okay, I have some more questions about the pseudocode. So it looks like you're only decrementing the hit counter when the ball runs into things, but that means that the ball is going to ignore the next hit counter number of collisions.
If any. It ignores the next hit number of steps, time steps, not collisions. Hit counter is decremented on every time step, not every collision.
Okay. And it also you don't seem to have any pseudocode here for checking if you run through the walls.
Well, we have to do that, obviously. You have to do that, yeah. No, if you look at the whole pseudocode, I think someplace in here, I talked about a more complete version. Not there. as entertaining as that is. So here is the full pseudocode where you do this computation of the interaction between two balls. Then, for each ball, you erase it, update the ball velocity, update the position, draw, using drag and wall collisions. So here, at order n, you do the wall collisions. I would say you ought to have a version of this code running for your own sanity. You ought to have a version of this code running next week. 2 balls, maybe 3 balls, not a lot of balls, but have the collision code running in your first lab. Because fall break is coming at us like a freight train 2 weeks from today. And the day you come back, Tuesday and Wednesdays will be due. So for fall break, the Tuesday lab, of course, doesn't meet because fall break ends Tuesday night. And so the Tuesday lab will be allowed to demo anytime Wednesday up until 7:30. So this needs to be done before you leave for fall break. Or almost done. The next lab, just to give you a small taste of this, we don't have a couple of more minutes. The next lab is, again, it's untested. I have no idea how hard it is. But it requires you build a fair amount of hardware. There's a motor driver you have to build. There's an instrumentation piece of this you have to build. But you also have to build the physical structure itself. I'm not supplying this. So you're going to have to build this beam hot glued to a potentiometer at this end and hot glued to a lift motor at the other end. And I would say if you're fairly efficient, it ought to take a half an hour. If you hot glue the shaft of the motor to the motor housing, you start over. So there's a little bit of care required. But there's going to be a lot of manipulation to do. So as soon as you finish Lab 3, start building the infrastructure for Lab 4. Lab 4 is primarily hardware. The software is going to consist of a PID control loop. Pretty straightforward to code. We're going to talk about that. But you're going to build a lot of hardware. So any last minute questions on the homework? Oops, too far back. Homework. Convert the vector notation velocity change equations in Lab 3 to scalar C code. I had some questions about that. One question was, are structs less efficient than arrays? What do you think? Let's say if you build a struct per ball, is that less efficient than having an array of velocities and an array of positions?
Well, your C compiler is going to convert that to basically an array. It just depends on how it packs it.
Exactly. How does it pack it? And does it need to do a multiply to get an offset? And it turns out that even if it does, multipliers are so fast on this architecture, integer multipliers are so fast that the penalty for using a struct versus an array is very small.
Okay, but I have a related question to this. So we're working in an environment where you can't allocate more memory. Everything has to be stored in existing global variables.
You can malloc.
You can malloc?
Yes, you can malloc. There's malloc in this C.
I'm not sure what it would do, but you can do.
Well, it takes a piece of the heap and turns it into whatever you want.
Okay.
But why? Why would you do that?
Right. So the reason I ask is I need to figure out what data structure we can actually store all these balls in, because the number of balls on the screen is going to be changing.
Yes?
So, like, the standard solution would be to store them in a linked list or something like that, but you can't malloc more memory.
You can malloc enough memory to do a linked list, but there's an easier way to do this. Let's say that you're always going to display all of the balls. In other words, you're going to traverse. There's never an invalid ball, but some of them may be off screen, in which case you don't draw them. So you have a big stack of balls down here at the injection point, and you don't draw them. You say, if it's off screen, don't draw it. When it becomes drawable, you move it onto the screen and give it a velocity. And then it's a static array, fixed size static array. And some C programmers are going to go, ugh, that's horrible, that's awful, that's such a waste of what? Who cares? It's an embedded system. You use all the cycles. Who cares? That's what you have to do in this lab.
Okay, we need to not detect collisions between those balls because they're all right on top of each other.
You're going to do nothing. If it's off screen, you do nothing to it. You don't update it, you don't do anything, you don't draw it, you don't erase it, you don't do anything. It's just, or you could have a separate integer flag saying valid, not valid. And if it's not, you have a separate binary flag saying it's not valid, don't do anything. Sure, that might be even faster than detecting the position. And as you go through the list, you're just going to convert them from valid to invalid. If a ball gets bounced off of this side of the wall, all you do is mark it invalid. Done. If it bounces off this side of the wall, it bounces, right? If it bounces off this side of the wall, it's just suddenly invalid, and you increase the score. If it goes through this wall, you mark it invalid, and you decrease the score. Get a couple of puzzled expressions here.
I thought we were doing a different game. You're not doing the paddle thing? I don't know. We do
The
have
paddle's moving here, it bounces off the paddle also, but if it goes off the back wall, it's gone. Now you want to make sure that when you actually drag a ball off the screen, that it never hits the line, because if it hits the line, it'll erase the line. And so you actually want to bounce it just inside the line.
If you try to write a ball to something that's off the screen, do you error out, or does it just not write it?
The people who wrote the library did bounds checks. So it doesn't error out, but it's a waste of time because it has to error check each pixel. So it's better to detect when you're near the edge of the screen and stop drawing it, or bounce it back, as the case may be. TA show up? Brian G had some homework, had some labs to hand back.
He was here at the beginning.
He was there at the beginning. He said he was going to come back at the end, but he has not. So you have to go find him. He's probably down in the lab, where I'll be in a few minutes.